Now Joachim Hebeler from KIT will present his talk. Yeah. Okay. So, hello and welcome from my side. I'm going to tell you today what we are trying to do at KIT, or in our research group, the Institute for Radio Frequency Engineering Electronics at KIT. How we try to teach our students how to learn circuit design and maybe go from simple schematics up to a tape out. We are, as the name suggests, an RF-heavy institute. We do RF circuits, everything from DC to 700 gigahertz, something like this. We also do a lot of system aspects, so we are not just circuit designers. We have people working on antennas, on packages. We have people on radar and algorithms. So as an institute, we are quite diverse. And that's a little bit also what we try to push then into our education. If we think about what is circuit design, then we probably think, well, people start as a schematic, they will go to a layout, we get a chip, and then they're done. But obviously, we're not done at getting the tape out ready, but we also have to think what happens after that. We might want to see the chip coming back, we want to measure it. We want to see how it performs, we might have to think how we put it in the system. So these are all aspects that we also want to teach our students, that you're not done just by submitting your GDS to the foundry. Going back a little bit and thinking about the term circuit design, especially what we talk about here in this open PDK context, what is it that we really want to do in this? And I brought here a chip photo. It's not mine, it's not any of yours, it's something that Analog Devices produced 2013. It's a 6 gigahertz SDR front end. And I took this picture because it's obviously full of different circuit blocks that many, many engineers build over many, many man-hours. And what we can see is that circuit design is rather a complex topic, very, very different aspects. And what we've seen today already is that we see digital stuff. We have very simple standard cells that are placed to the millions on a chip, and where the biggest part is writing your RTL and getting the pipeline running, that the computer is doing all the work for you. We've seen some analog stuff where people try to optimize their schematics, try to get all the capacitances out of their layout, make sure it works. But we also have all this RF domain. And if you look at the left, the RF part is more or less the biggest part of this chip. However, on the RF part, there are probably like 20 transistors, or like, with all these front ends, 100 or 1,000. So we don't talk about circuit complexity, but we talk about layout complexity. People have to think about how do they set up all these layouts, because RF means we have to take all these little shapes into account for what we are doing. So overall, that means that if we go into circuit design, then we have all these different topics that are more or less whole groups, whole companies just concentrating on one of these. So obviously we cannot teach everything. So we just concentrate on RFIC. But even if we go into RFIC design, then we have also these little sub-blocks that we have to sort of think about: schematic, design verification, how do we even set up a workflow, how do we work on these things? And big companies probably have whole teams just considering some of these aspects, thinking about how to do this efficiently. Again, we cannot teach a student all of this. We have to concentrate on some, but it's somewhat of our desire to tell a student, hey, this is the whole picture. If you go into a company, you will be exposed to all of this. You might not do all of this. You don't have to do all of this, but this is the whole picture. And you can pick some aspect of this that might suit you. But right now, we want to concentrate on schematic layout, design verification, getting something, doing some EM simulation, stuff like this. So how do we try to teach circuit design at KIT? Well, basically we start with some elektronische Schaltung, intro into electronics, how does a transistor circuit work, the basic stuff. Then we have a lecture going into RF electronics, teaching what is transmission line matching, how does reactive matching work, getting the students to build a 2.4 gigahertz amplifier on a PCB with a discrete transistor, getting on a network analyzer, measure it, see does it work, does it not work, see oscillations, maybe fiddle around and realize, okay, there are all these different things that we hear, stability and loop gain and whatever, that these are real effects. And we want to get students hands-on experience. They shouldn't sit there and be like, my curve now looks nice, but they should be on the bench measuring their stuff and see, I designed something, I got a completely different outturn, somewhere in the process I made a mistake and I have to learn from my mistakes to make it better. Next, we want to teach students RFIC design. Circuit design nowadays is all on chip. No one builds complex circuit on a PCB anymore. I mean, ideally today you have one chip on there with a bit of power supply, a few connectors, that's it. So circuit design is on chip. So we want to teach students how this is work on chip. And lastly, and this is the one I will show some results, we have a design lab, which is somewhat of a hybrid between a lecture and a lab, where we try to teach students how to build your own MMIC or RFIC, how to do chip design, and actually get them on cadence, get them to make circuits, make layouts, hopefully get them to tape out and actually go through all these steps. There are a few other lectures that we have that are not mandatory lectures, where we cover mixed signal design, VLSI, stuff like this. Nothing I can talk about today. If we go into our aims again, I mean, we want to expose these students, of course, to RF circuit design concepts, and that's, again, also something that we have to think about OpenPDK. We want to address a lot of new people that have no access before. They probably never had any sort of introduction to these concepts. We already heard some stories where people just started out of the blue. They obviously don't have these sort of lecture that to guide them through there. So again, if you think about OpenPDK, that's also something that we should put in there, that we should expose all these new people to these concepts, ideas, workflows, history that is necessary to understand this. What we also want to teach is, we want to teach them with tools, processes, technologies that they will actually encounter in their life. We don't want to take some 1 micron CMOS process and get them to build an op-amp with 5 transistors and be like, now you can do circuit design. Because that's not what happens anywhere. I mean, if you go from this to 22 nanometer, it's a completely different world. You will just have a very hard time. No, we want to teach students with real-world circuit design. And for this, we currently also use G2, because it's a very high-performance technology. We can showcase all these RFIC aspects. And a lot of stuff that you learn there, layouting, geometry, it's something that's important also in every other technology node concerning RFICs. We also want to teach them with current topics. We don't want to have artificial, synthetic things, or please design this amplifier for these virtual specs. We want to teach people, why do we work on this? Where do we work on this? Where does it go? And I mean, current topics are obviously 5G, 6G, base stations, smartphones, interlinks. There's a whole world just revolving around 5G and 6G right now. We have all these radar groups working currently on 120, 140 gigahertz radar systems. It's a very interesting topic, and it's something that's very interesting in the future. Next-gen communications, joint communications and sensing, some very high-speed optical fiber links. There's a lot of stuff that's in there that we want to teach students, that there is this whole world, this whole industry, this real immense market going there. So to sum it up, we want to teach our students real-world engineering. We don't want to have some artificial lab. We want to show them how do you actually build something that's real-world. And we want to let students actually get hands-on experience designing real-world stuff. So we have this lab, and I have here just the list of things that we try to teach them, to where we think this is important for them to understand, to get into circuit design. It's a quite exhaustive list, and I mean, 12 or something points. I think the major points here is we want to give an overview about chip design, like how do people approach the system aspect, how do you approach component level aspects, not on a very in-depth stuff and calculating stuff, but rather understanding why do people go like this, why do you see this topology in a paper, why do people not choose another topology, why don't they use PLLs at 200 gigahertz, why don't they use a super heterodyne receiver anymore, stuff like this. Why do you see this stuff? That's we want to get there. Another big part is teaching them how their tools work. We try to teach them how does an EM simulator calculate this EM simulation, how does the circuit simulator calculate a DC solution, or the AC solution, or what is harmonic balance. Because what we see in our practice as PhDs is that we push these tools to a certain limit. And we're talking about cadence and battle-tested tools in a way. Even these tools will at some point produce strange results, oscillations where there shouldn't be, some weird drift, convergence issues. And they obviously generate these results because they are fundamentally just solvers for some math. And we have to understand what is the theory behind it to understand why does my circuit currently not work? And why does the output look like this? That we as designers can have confidence in our results. Because if we just optimize for, oh, this is a nice looking curve, then obviously we omit all these things, and in a very bad way, you just design some crap. That's something we don't want to do. We want to teach them how does your tools work. We also want to talk about all these secondary stuff. What's the substrate effect? Why do we care about this? Why is there something happening? What is thermal effects? Why do we care about this? Are these common centroid designs? Why do people fill their wafer up with dummy transistors? Why does this all happen? It's stuff that's not really necessary for RF design. You can just build your amplifier and be done with it and just click the filler generation script and a working circuit pops out, hopefully. But again, we want to teach real-world circuit design. These are real-world effects. It is real-world stuff that they have to think about. And especially they do their master thesis and the next day want to start as a PhD, they have to think about these effects anyway. So we want to expose them. And lastly, we also want to bridge the curve and show how could you do digital design. We don't want to get them to do digital design, but we want to say, if you want to go there, this is how you do it. How would you approach mixed signal design? We don't want to go in there, we just want to say, there's a way to do it. And of course, what do you have to do to even do a tape-out? I mean, you don't design a circuit, send a mail to IHP and say, please make me this circuit. No, you have to do a bit more than that. So, and what are the results? Well, we had some groups. There's the group of 4 people that built a 28 gigahertz hetero or homodyne IQ receiver. This is an SG25H3. This we did in 2021. Interestingly enough, we also have the matching 28 gigahertz transmitter, also homodyne. This is a group of 2 people, or 3 in the end. And they got these circuits manufactured, did the tape out. Obviously, I did a lot of helping there to get them to up to snuff, because tape out is something that's a lot of knowledge-based rather than understanding-based. So there's a lot of help in there, but all of what you see here is students' work. They designed the circuits, they did the simulations, they built these chips. Obviously, I said it before, I mean, the world doesn't stop by sending this to tape out. So we also tried to measure these chips. This was a measurement that we done with the students themselves, where we set it up. And again, at some point that we have to think about an open PDK. We give people free access to tools, free access to the tape out. And then they have a chip and they want to measure it. And I mean, we have a table here now with like 150K of equipment. And those people who didn't have this stuff before, because they obviously didn't, otherwise they would have done circuit design, they now are at the problem that they also need this equipment. So somehow an important point in open PDK would also be open measurement, or the access to labs where you can measure this stuff. Also another thing, we measured this chip, and obviously the world doesn't end if you tape out. We measured it and realized it doesn't work. Again, LVS is clean. The tape out is exactly what the schematic looks like. DSC is correct. EM simulations were correct. But still doesn't work. And why didn't it work? Well, the students made a major oversight and built an AC coupling capacitor in their baseband path. I told them that they should not do this. I overlooked this as well. And in a way they didn't. They have a 2-stage amplifier design. The first stage is DC coupled. The second stage isn't. It's AC coupled. So what we saw in measurements, we put a pattern on there. We have a high-pass filter. Patterns doesn't work. What they did very well is that their baseband amplifiers are very wideband. They go up to 2 or 3 gigahertz. So we just shifted the baseband signals a little bit and did some signal magic and could see, okay, there are some patterns. We see 800 megabaud QPSK, 120 megabaud 16 QAM. So in a way, the system actually works quite well. The other problem is, it's here, or here. The PA has no output power. We measure like minus 20 dBm. Again, LVS is clean. The schematic was fine, but somehow this first stage is broken. Because, I mean, it's RF design. You have to think about all these inductors. An inductor is just a piece of wire. The LVS doesn't care if this piece of wire has 2, 3, 5, 10 turns, but the amplifier cares. And somehow this first stage amplifier doesn't work. Well, what you could measure was like the leak-throughs through the amplifier and then just measure the output and see there, okay, the pattern is there, so if the amplifier would work, this would also work. What we also tried to do, we built these nice modules there and tried to put it on a table and put some antennas there and just see, can we just get out some measurements, because I wanted to test this receiver and we didn't have some up converter to put an RF signal on there. But because the output power was so low and some other issues, I couldn't get a proper result. This was from last week, so it's not really possible for me to show any results for the receiver, so I can still hope that it will work, or maybe not. But again, this is a very important part. Coming to somewhat of a conclusion, where would we see open source in teaching, or where should open source fit in? And currently what we have to think about is we teach tools by availability. We are members of Europractice, we have access to Cadence, we have access to Cadence classroom licenses. Cadence is the tool we use to work as an institute, so that's what we teach our students. We also have access to AMX and Mentor Calibre and Keysight ADS and CST, so that's the tools that we want to teach students. If there's an open source flow and open source tools, and we see, okay, we can actually work with open source tools, we can use them to make our RF circuits, then we might also teach our students how to work with this, because it's obviously easier. Right now we have to get people signing an NDA, we have to look for other factors. Another factor that's more or less interesting is export control, because we are oftentimes told, oh, your amplifier works at 30 gigahertz, now we have to make sure that it isn't sold outside of Germany, and certain nationalities are not allowed to have access to it. And that's something that maybe should be evaluated with some open source technology and these things, how this works. Genau. And also one point, what tools can actually replace commercial tools? I mean, having all these open source tools is nice, but can they actually replace something? Can they replace AMX? Can they replace ADS? Can they replace Virtuoso at some point? For the digital side, it seems like it's very well possible to do tape-outs without using Innovus or Genus or some of these tools. But for the RF side, so far I've seen it's not on a maturity level that's suitable. Also some points from my side. What would I need for a tool that it works? And I mean, one very obvious point is easy PDK integration or overall easy integration. I mean, we've seen the presentation from Linz. They have a Docker image with 40 different tools. If I have to install all them manually, that's a no from me because I don't want to deal with all these tools and then look up, oh, they have a new version or the version is too old or there's some fork that I missed or something. I want to have something that's easy to use because I want to design chips and I don't want to do software. And that's also true for the PDK. It should just work. I just put it in there and then it should just work. I don't want to mess around with scripts. I don't want to set up an environment just to do the reference flow. I want it just as it works. We need, of course, all these solvers. We need all these nonlinear solvers, and they are somehow quite mature, but I've heard harmonic balance is still not really there. Envelope simulations, very complicated simulations. We have done EM simulations with 200-port S-parameter matrices simulating very large circuit blocks. Of course, that's a very big problem for S-parameter simulation because then all these residuals can accumulate to large errors. Does these solvers handle these super large models? Can harmonic balance run off these super large models? Is this possible for our research, or is it more or less you can build 2 transistors and simulate some transmission lines? Also for this layout design, LVS, QRC extraction, very big features, very necessary. EM simulator integration. In our RF reference flow, we do an extensive lot of EM simulation. We EM simulate everything more or less. I mean, if people could, they would simulate from pad to pad. I mean, some trial just takes ages. And DSC checks, it's not just a point, but we want to have the DSC checks that the fab will also do. We have seen in the past that there were issues with communication and documentation that we used one tool for DSC and another tool was used by the fab. You send your layout out, you get a list of errors back, and you're wondering where do they come from? Because you're not just fixing some small bugs, you have to change your layout and you have to do all these reference checks again. Does everything work? Does this additional metal you introduce somewhere influence something? It's a whole lot of work we have to do, so we want to have very trustworthy DSC checks for our layouts. And lastly, some wish lists. Python integration, I like Python very much. I think it's the language to go right now, other than Skill or something like this. If there's some interface and we can just write scripts, would be very nice, plugging in there. Can think about all these different stuff. Interoperable formats is something very important for me. I don't want to have a flow where I export something, re-import, and then have a converter script and having like a copy of the same thing in 10 different formats, and then something fails and I never realize it because there's still this artifact from the last time. And I wonder why my parasitic extraction is wrong because somehow this layout wasn't updated, stuff like this. Cadence and ADS does it very good with this interoperable format. You can just use the same layout in Cadence, in ADS. You don't have to change anything. That's a very big plus. You can take the same layout that you want to send to the fab, open it in ADS, open it in EMX, press simulate. You don't have to modify it. There is no error you can introduce. That's something important for us. Also automation, clearly documented workflows. I want to understand what I have to do, not try to skim through 1,000 pages of documentation and scripts and be like, hey, do I have to do this? What do we have set up? Integrated environments. I don't need one UI, but I need something like this Docker image where I can just get the whole environment, press play, everything works, and not install that, install that, install that. Oh, there are 5 different tools that are similar in some range, but also different, and some are not developed and others are, and you have to spend 2 weeks just figuring out which tools are good or not. That's so far from my side. Any questions?